Today we're going to finish section 1.4. Also a couple of reminders. So you have homework from 1.4 due on Friday, the web assign and written work. The written work problems, I mentioned them last time, but just as a reminder, they are on page 83, and it's just problems 96 and 97. It's 2 problems, okay? And I'll show you when we get to the part of the lesson where it's problems like these, kind of like that I did the last time, where you'll realize probably pretty quickly why it is that WebAssign doesn't do a great job on that kind of a problem. And then also on Friday, you have a quiz. So another reminder is that out inside of Canvas, there are practice quiz questions. So if the first quiz caught you off guard, you weren't quite sure what it was going to be like, and then it didn't look like what you expected, or you want some extra practice, please make sure and take a look at the practice quiz questions, in particular for sections 1.3 and 1.4, because that's what the quiz will cover. Okay? Shall we get started? So last time we started section 1.4, and we are talking about continuity and one-sided limits. And in particular, what we actually looked at last time was we talked about the definition of continuity, but then we actually did some examples of one-sided limits. And the examples of the one-sided limits came about from the perspective, if you will, of, hey, these really aren't a lot different than two-sided limits. I just only have to consider one side. So we did them algebraically. So we were just evaluating by plugging the number in. If you were doing it graphically, we've thought about how that would work. You just come at it from one direction, from one side on the graph. We've done that before. And then we didn't really talk about it numerically, but you can do it numerically as well. So to do it numerically, it would simply mean your table would only have half the number of values. So when we did limits numerically before, we had the limits from the left and we had the limits from the right, and you just do one of those sided limits. So on this one, for example, if you were doing a table, right, if a problem asks you specifically to do that, sorry, that's from another class. Let's try that again. You would only do values that came from the right-hand side of 8. In other words, bigger values than 8. So 8.1, 8.01, and 8.001. You simply wouldn't have the other side. So that's what it would look like if you were doing a one-sided limit numerically. So let's actually move a little bit more into this idea of continuity that was also in this section. By talking about discontinuities. So when we have continuity, we defined it loosely last time, verbally, as this idea of being able to sort of draw the picture without having to take our pencil off the page, at least nearby the points we care about. But there are 2 types of discontinuity that we can also have. So one type of discontinuity is called a removable discontinuity. This occurs when f can be made continuous, by appropriately defining or redefining f of c. And visually what's happening when we have a removable discontinuity is we have a hole in the graph. And we've talked about algebraically, when is it that we have a hole in the graph? Well, when we did it algebraically, it happened whenever we tried to plug the number in and we got 0 over 0. And then when we factored things out, it went away. Hence, it was removable. Okay? So we have the ability, algebraically speaking, to remove the problem that's causing the discontinuity. We'll talk about this redefining business in a minute, but that's what's happening sort of visually. A non-removable discontinuity occurs when f cannot be made continuous by redefining or defining it. So visually speaking, if you have a non-removable discontinuity, you would have either a jump in the graph, or you would have an asymptote. Most of the time when we're given an equation, it's an asymptote because we see the denominator equaling 0 when the numerator doesn't. That's typically what happens. In order to get a jump in the graph, we have to have functions that are defined piecewise. So we're going to encounter a piecewise function later on. It's in example number 6 at the bottom of this page today. But jumps only occur when we have piecewise defined functions. So we're going to take a look at some examples where we have to decide if the continuities are removable or non-removable. And we're going to write down also what's happening visually there that we know, because sometimes your questions will involve that component too. So if I were to take a look at this one, it wants us to find the x values where f is not continuous. Right, problem spots, values for x that cause me problems, and then to decide if that problem spot is a removable or a non-removable discontinuity. So in particular, when you're looking at this, what x value can you not have? Yeah, x equals 0 is a problem spot. It would make the denominator 0. So this is not continuous. I'll write it afterwards. At x equals 0. Is it a removable or a non-removable discontinuity? Yeah, it is non-removable. So several of you answered very quickly. Would one of you tell me why you believed it was non-removable?
As it's like approaching.
Yeah, say that again a little bit louder, Abby.
The numerator's not 0.
Yeah, the numerator is not 0.
So, and if you think about it, as it's approaching 0, it would just be getting closer and closer to 0, but it would never reach it.
Well, it won't be getting closer and closer to 0 as x approaches 0. It actually be...
X is approaching closer to 0, like it would.
Yeah, as x is approaching closer to 0, we actually will get values that get infinitely large.
Yeah.
Like infinitely big if it's positive or infinitely small if it's negative. So, because there's an asymptote. I mean, all those things are playing into it, right? All those are reasons why this is going to fail to be removable. So it is non-removable, and if I were to justify or to talk about why, there's lots of things you could say that are all appropriate. You could talk about because the numerator, so we'll put down the first one that was said, the numerator does not equal 0, but the denominator does. That's one reason to talk about it being a non-removable discontinuity. You can talk about it from a graphical perspective because there's an asymptote there. At x equals 0. Okay, so that caught the one that Abby mentioned, and it caught the one that Elisa mentioned. And the one that Joel mentioned, this idea of plugging in numbers, that's that third approach that we've had, the numerical approach. So from a numerical approach, so if x is approaching 0, like the numbers themselves are getting closer and closer to 0, then 6 over x is either approaching infinity or negative infinity. Right? I'm getting values that are getting infinitely large or infinitely small, and you can think about them from a table perspective. So any of those are appropriate justifications as to why this is actually non-removable. Good job, guys. Let's do another one. This one is not quite so quick for us to look at it and say the x values where it has problems. What am I going to have to do?
Factor.
Yeah, let's factor the denominator. Okay, so somebody tell me how to factor the denominator. Good. X minus 5 and x plus 2. Okay, is everybody good with that? Okay, do you see anything eliminating or canceling out? Yeah, the x plus 2's. Now, when that happens, it doesn't eliminate the fact that there's a problem at x equal to negative 2. There's still a problem there, right? I still can't plug x equal negative 2 into the original function. So there are two discontinuities. There's one of them at x equal negative 2, and there's one of them at x equal 5. But different things are happening on those two at those two locations. So these are the places where it's not continuous. So that's my actual first question. I was already jumping to the second question. Let's talk about the one that we canceled out, the x equal negative 2. So is that one removable or non-removable? Removable. I mean, we actually removed it, right? And again, you can justify it from any three of the approaches that we used. So the algebraic approach is the idea that it was 0 over 0. I canceled it out, and now I can plug the value in, right? You can do that. So that's a graph or a algebraic approach. 0 over 0. And I can factor and evaluate, actually. If you factored this like we just did, and then you simplified it, I didn't write that simplification down, but I want to use it for something in a moment, so let me write it down. Could I plug in x equal to 2 now? Yeah. What would I get?
1 over
1 over negative 3, or negative 1/3. So I can evaluate the limit, and it will be equal to negative 1/3. That's what algebra says I'm able to do. If I look at it from a graphical approach, what happens here? There's a hole. Now, it's interesting because the hole itself has a location. And in fact, if you look at it on your calculator, you won't see a hole. Your calculator cannot handle things with precision like that. It doesn't sort of draw a hole in. And I think you know that sort of intuitively, that you've never seen that on your screen. But there is a hole if you're tracing it along and you get to x equal to 2. What will actually, is it 2 or negative 2? Negative 2, sorry. X equal to negative 2. What your calculator will actually do is it will say x equal to negative 2 along the bottom, and then the y value will be blank. It won't say anything. But if you watch the x values and the y values as they get really close, the y value will be getting close to that negative 1/3 that we've just noticed. So actually at the value negative 2, negative 1/3, there is a hole there in the graph, whether your calculator is showing it or not. Your question?
If you put -2 minus 5, is that not negative 7?
It is. Sorry, I didn't catch it as people were giving me answers. I'm sorry, you're right. This should be negative 1/7, so let's fix that. Not negative 1/3, negative 1/7. I didn't have those details written down because we could just do it together. And then we made a mistake. It's okay. It's all good. So negative 1/7. Thanks for catching that. And then if you're doing it from a numerical approach, right? As x is approaching the negative 2 value, then y, from both directions, will approach, that's the arrow, means approaching, will approach a negative 1/7, which is harder to see necessarily on a numerical expression, because 1/7 is not a number that we probably have memorized, like the decimal expansion for. But we could find it from an algebraic approach pretty easily, like we just did, as long as we don't make a mistake with our negatives, of course. What about x equal 5? What happens at x equal 5? Yeah, it's an asymptote. So it is, the first one is removable. The second one, number 5, at x equal 5, is non-removable. And I can almost write every single thing I just wrote over here down, right? It's non-removable because the numerator does not equal 0, but the denominator does. So numerator is not 0. The denominator is 0. From a graphical approach, there's a hole, an asymptote at x equal 5. And from a numerical perspective, if I try to let me say as x is approaching 5, the y values, depending on which side you're approaching from, will either go to a positive infinity or negative infinity. And it really doesn't even matter. If they both went to positive infinity, it still would be an asymptote, right? So you've seen asymptotes that do this before, yeah? Where right here in the middle we've got, okay, it's not a great picture, but we have the asymptotes both going to infinity as we get close to the asymptote. So that's still a possibility, but this one happens to have different values. So one side goes up and the other side goes down. So it looks much more like this at 5 instead. This is not drawn to any kind of scale or anything, just imagery for asymptotes. Okay. So lots of justifications of what we can think about in terms of removable or non-removable for these particular locations. A little bit more about limits. If we have a function f and c and l are real numbers, then the limit of f of x as x approaches c is L, if and only if the limit from the left is L and the limit from the right is L. And we've seen this before, just not written quite so precisely, right? So if you approach from the left and you approach from the right and you approach the same location, then the limit exists, and if you approach different locations, it doesn't, right? We're eliminating the ability to have a jump in the graph is what we're really doing by the way this is defined. The left-hand side and the right-hand side have to approach the same place. So what we're actually going to do on the next example is we're going to take a piecewise function. So in other words, a piecewise function has the ability that it could be disconnected, right? Yeah, because the two pieces don't have to be defined so that they match up. But we're going to make it defined so that they do. So you'll notice that this function, it says actually find the constant a such that the function is continuous on the entire number line, or the entire real line. And 3x squared doesn't have an a in it, but the other one does. It says ax minus 4. So in order for them to approach and actually be the same value, it means that this place where they're getting close to, namely at x equals 1, as x approaches 1 from either direction, they both have to get to the same spot. I can't have this jump going on. I have to approach and hit the same location. In other words, I want the same y value. As they both approach the value of 1, x equal 1, I want to make sure that they have the same y value. So what we're actually doing, and we'll do it very precisely, is we're taking the limit as x approaches, is it 1 or negative 1? It's 1. As x approaches 1 from the left, and the limit as x approaches 1 from the right. And we need to make sure we're looking at the right equation. So depending on the intervals over here, it tells me I should be able to decide which one's actually the left-hand side of my graph and which one's the right-hand side of my graph. So looking at 3x squared, is that the left side of my graph or the right side of my graph? It's the right side because it says x bigger than 1, right? These are values that are on the right-hand side of my graph. So this 3x squared is what's happening when x is bigger than 1 or to the right of 1. The other one, the ax minus 4, is the values that are happening when we are to the left of 1. So we're taking the limit as x approaches 1 from the left of ax minus 4 and 1 from the right of 3x squared. And we're doing it again from an algebra perspective, which we established last time we're allowed to do, even when we have one-sided limits, by just plugging the number in. Substitution. So a is the variable that I'm looking for, so it doesn't change, but the x value is 1 for the first one, and the x value is 1 for the second one. So far, so good? And I'm just simplifying. So this one is a minus 4, and this one is 3. And what I really want is I want these quantities to be equal. So I just need to find an a value that makes them equal. In other words, when is a minus 4 equal to 3? Yeah, when a equals 7. That's really all the question's asking me to find. But with some precision, right, we're going to be doing these kind of pieces if we're working on it, like on a written work problem or something like that. I can't remember. I don't think the written work actually includes this on this one, but I could be wrong. I think it's going to include the next part only of what I'm showing you. If you were doing it on a test or something like that, you'd want the precision showing that you've tested both pieces. You have a little bit more flexibility and a little bit less precision when you're working online, of course. So. All right, a little bit more about continuity, and then we're going to shift gears slightly to an application of continuity. So the last time we talked about the definition of continuity, let me just flip back over so you see that we did it. We did the definition of continuity, at a point, and then we expanded it to be on an open interval, which we just said, okay, it's for every point in that interval. And this last definition of continuity tells us what happens when we are on a closed interval. All right, so if it starts to feel like, didn't we already do this? I mean, a lot of it matches. That should make sense. But there's some additional pieces that we didn't have before. A function f is continuous on the closed interval bracketed ab, right? That means it's closed. Just means it includes the endpoints. When f is continuous on the open interval ab, which we talked about before, and the limit of f of x as x approaches a from the right is f of a. All right, so if we approach this value from this side, so we're moving in that direction, it's the same thing as we would get if I plugged in, the a value for the function. And if we do it from the left-hand side, we're approaching this b value from the left-hand side. It has to be the same thing as what happens when I plug b in or substitute b in for x. The function f is continuous from the right at a. It's continuous from the left at b. So what are we trying to eliminate? Well, we're trying to eliminate the ends having asymptotes. That's really all we're doing. If the ends have asymptotes, we would not say it's continuous because you don't actually have a function value on the ends of the graph. Practically speaking, those are the eliminations that we're having happen here, is that it has a specific value on the left and it has a specific value on the right. We're not trapping something between asymptotes. Properties of continuity. So you've seen some of these properties already with limits, and since continuity is based on the idea of limits, it makes sense that these properties come sort of almost for free as well. So if b is a real number and f and g are continuous at x equals c, then as long as we have a function that is already continuous, if I multiply it by a number, that's what this is, a scalar multiple, it's still continuous. If I add and subtract two continuous functions, they're still continuous. If I multiply two continuous functions, they're still continuous. And if I divide two continuous functions, they're still continuous. The only caveat on the division one, of course, is, once more, we can't have the denominator equal to 0. These are all the same as the limit processes that we had before. All the properties, the same. Because continuity is based on limits. Everybody catch that one? And had a bit of writing. So this is an application of continuity. That's why it's not in the title of the section, actually. Intermediate value theorem. And I'm pretty sure that both of your questions in your homework, the written work, are these problems. They're intermediate value theorem problems. So if f is continuous on a closed interval ab, okay, that's the definition we saw just a moment ago, and the end points, f of a and f of b, are not exactly the same. Okay, what is it saying I can't have happen? Well, I can't have the two end points be at the same y value for this to hold. So I have to have one of them higher or lower than the other one. That's all it's saying. They're different. Okay? And k is any number in between f of a and f of b. So let me put this on a graph so you can kind of see what it's saying. So here's a, and here's b. So this is the y value, or the f of a value. And right up here is my f of b value. And it doesn't matter if a is higher, the f of a is higher than f of b. That's absolutely irrelevant. Okay? Doesn't make any difference. And they're saying if there's a k value somewhere in between them, anywhere between f of a and f of b, that somewhere, if I have a continuous curve and I'm going from the left-hand point to the right-hand point, somewhere I have to have a corresponding value that's got a y value of k. I can't sort of jump over it. Why not? Well, because if there's a hole in the graph, it's not continuous, right? If there's a jump in the graph, it's not continuous. I have to actually hit every single y value between f of a and f of b. That's what it means to be continuous. So there's a space between each of those where I have to hit. So it's not hard to show this, but it's hard to do it in an electronic form, which is why you're going to do a couple problems that are written. And let me show you what they look like. So this one says to verify the intermediate value theorem applies. So to verify that it applies, we have to have a few pieces. Piece number one is we have to show that the endpoints don't match. Because you can imagine, of course, if the endpoints match, then there isn't any point k between them, right? There just isn't. So we have it all just collapses and it becomes sort of a silly statement. And then it tells us that the k value is between whatever f of a is and whatever f of b is. And the other statement, I'm sorry, I skipped over it, was that we have to verify that we have a continuous function. Okay, so my continuous function is going to be the first thing I'm going to justify. The second thing I'm going to justify is that the endpoints don't match in their y values. And then the third thing I'm going to justify is that my k value that I'm given is between those endpoints, the y values of those endpoints. Those are my three verify statements that I have to do. And then I'm going to use this theorem to show that it really works and to find it. So here's my equation. I've got x squared minus 7. I think you know what it looks like in general. This is a parabola. So we've got a parabola here. And the first thing that we need to do is to justify that it's continuous. Now, the cool thing for the ones that we're working with is that we almost get it for free, but we don't want to sort of gloss over the fact that it's true. So we want to justify that our f of x is continuous. And our justification for why we know that's true comes from a previous section of material, and it's because f of x is a polynomial. And we talked about the fact that all polynomials are continuous. So we also talked about radical functions are continuous. We even talked about rational functions being continuous as long as it doesn't include anything that makes the denominator 0. So if I had something that made the denominator 0, it's simply not between 2 and 3, and it would still work. So you have to make a statement that says it's continuous, and the reason why is because of it being a radical, a rational, a polynomial, whatever. Okay, you have to say that. So that's verifying the first statement. The second statement talks about what happens at the end points. So I have 2 and I have 3. So we're going to find f of 2, and we're going to find f of 3. You don't have to necessarily show me the work for that. You can probably do it in your head. But if not, this is what we're talking about. We're doing 2 squared minus 7 and 3 squared minus 7. So what is 2 squared minus 7? Negative 3. And what is 3 squared minus 7? Yeah, it's 2. Okay? And in particular, these do not equal one another. That's what we're shooting for in step 2. They're not the same. And then step 3 is a very simple statement that the k value that they're having me look at actually lies between these two values that I just found. And does it? Yeah, it does. So our negative 3 and our 2 that we just found do in fact have between them the number 1. So we're stating that fact too. So number 1 is really a statement, and number 3 is really a statement. It's a statement that says, I've observed that this is true. I thought about it. Okay? Statement 2 requires a tiny bit of work, a little bit of algebra stuff back from like algebra 1 in high school. Okay? Easy stuff. And then what we're going to do then for the rest of the directions is it says, use it to find the value of c. So I know beyond a shadow of a doubt that between the x value of 2 and the x value of 3, there will be a location when x squared minus 7, my function, is equal to 1. There has to be. And I'm going to find it now. Now, it's a quadratic, so you have lots of things you could use. You could use factoring, if it works. You could use completing the square. That will always work. You could use the quadratic formula. Or on this one, it actually works really nicely to use the square root principle. That doesn't always happen. But because this doesn't have a linear term, it's just got the x squared and the constant, we can move our 7 to the other side and sort of solve it directly. I'll take my square root. So my x value is positive or negative. 8 factors into 4 and 2. The square root of 4 is 2. So 2 squared is 2. But I need to be a little bit careful. Those are the values where this function is equal to 1. But those are not the values for c. Only one of them is. Which one do you think c is? Right? This is 2 values, right? One of them is negative 2.
The range cuts off at 2, and 2 square roots of 2 is higher than 2.
Okay. Okay. So we need to figure out, let's just look at a decimal approximation for it to make our decisions, because I think that will help us. Somebody put 2 square root 2 in your calculator. What does it give you? 2.80. So it's approximately 2.8. For the purposes of what we're doing, that's plenty enough accuracy to go with. And the other one, whoops, did I get, that one's the negative one. And the other one's 2.8. So one's 2.8 and the other one's negative 2.8. It's possible, in a general problem, that both of them are c values. Like that could happen. You could get 2 values and they're both on the interval. But that doesn't happen here. Now keep in mind what our interval is. Our interval is right up here. We're looking for values between 2 and 3. So it's just the 2.8. It's really easy to get confused about what intervals I'm looking at. Am I looking between 2 and 3, or am I looking between -3 and 2, right? But the x value that I was given was already between the -3 and the 2. That's an x value. What I'm finding out right now is I'm sorry, that's a y value. I'm sorry, I said that wrong. Those are y values. What I'm finding right now is an x value, and it needs to be on the interval that I was given. That's the 2.8. So the c value that I'm looking for here that I knew had to exist and that for sure does exist is actually 2 square root of 2. And of course that approximation, just as a reference point, is 2.8. And just so that you have this in your notes when you look back later and you're like, how did we decide that again? It's because that 2 is less than my 2.8 is less than my 3. And that came directly from that interval that I was given at the beginning. So that's the c value I was looking for, 2 square roots of 2. Now notice, if my interval had been larger, like instead of my interval being between 2 and 3, let's say my interval had been from -3 to 3. That'll be okay. In fact, it will even satisfy everything. -3 to 3, it's definitely continuous because it's a polynomial. If I put in -3 and I put in +3, I'm sorry, that one won't work because then the next part's going to fail. Let's use -4 and 3. If I put in -4 and I put in +3, these two won't be equal, right? If I put in -4 and +3, they won't be equal. And sure enough, they will still be giving me values where the 1 will be between them. And I would actually end up with two answers that both did work. So it's completely contingent upon the interval as to which of the answers, or maybe multiple of the answers, will work in your particular problem. Any questions on that? Yep, Joel.
How exactly would that work if it was an equation that wasn't continuous? Or like, would you just like graph it and be like?
So, any of them that are asking you this way, notice the way that the question's asking, they're already telling you it's continuous. Because they say to verify that the intermediate value theorem applies.
Okay.
They're telling you to verify it. In other words, they're telling you it applies. You just tell me why it applies, and then you'll be able to continue. So you won't have anything that where it does not apply because of the structure of the language of the question.
So like, if you had like an equation where the entire graph wasn't continuous, but that's where the range was?
Yeah, so that's a good question. You could still do that. So let's say, let me just make up something real simple. Let's say that you had like 1 over x. Definitely not continuous at x equals 0, right? But the interval that you're looking at is actually like from 1 to 2. So this is still continuous because it's a rational number, and the only issue with the domain is that the x can't be 0, and 0 is not in my interval. That's how you justify that first point. And then you go on with the rest of it just as like before. So the justification would look slightly more verbose, like you'd have more words in it, because you'd have to explain why it's okay. But it still would be okay. And it is because it's a rational function still. Okay, I know that 1.4 is complete. I'm going to keep the video rolling just because we still have a couple people that are gone out, and if they look at this later, I want them to hear this. So 1.4 is over, but what I want to sort of preface you is coming up is you have the quiz, of course, on Thursday or on Friday. A week from Friday, you have a test. You do have a test coming up. For some of you, this is your first college math class. I know that's true for maybe a third to a half of you. For some of you, that's definitely not true. But I do want to throw out here this idea that, especially for calculus, and even if maybe you didn't even do it in previous math classes, choosing not to study for a math test, which is probably what you did in high school because you could, is probably not a best choice for a college class. So as you're thinking towards that, we're going to do a review in class on Wednesday next week. We're going to talk about what's on the test. I have printouts that I'm going to give you of things you can think about and study from and so forth. But between Wednesday and Friday next week, you're going to study, at least, between those, or you're probably going to find your test results not look anything like what you've seen before when you haven't studied. It's going to be a problem, okay? Also be prepared for the fact that at some point between Wednesday and Friday, so either Wednesday night or Thursday night, hopefully we hope for Thursday night, they'll have a review session for you with one of our math tutors in the Success Center. They'll give you time, they'll give you a location, and they will work with you on questions. They'll talk to you about things that you should prepare for based on their experiences. Most of them have had calculus here at OBU, not all necessarily, but most of them have, specifically this course for myself or someone else. And they'll be able to kind of guide you with some ideas about what to expect on that test from a student perspective, okay? So that's coming up. Plan for the fact that between next Wednesday and next Friday, you're going to be studying for a math test, even if you've never done that before. All right? We're done early today. Have a great day, guys.